Welcome to qnawire.
A car in an amusement park ride rolls without friction around the track. The car starts from rest at point A at the height h above the bottom of the loop and treat the car as a particle. So the path here the car is going to take is going to go down here. It's going to go up to point B, down to point C, and around the loop. So here the circle has a radius of r. But what we're going to do is we're going to find the minimum value of h in terms of r, such that the car moves around the loop without falling off the top. So since it's a minimum, what we're trying to find is we're trying to find a point at which it just reaches this point and goes back down. It doesn't careen into B, and B is forced to put a force on it to push into a circle. It doesn't get up to this, and since we're trying to find the minimum, it has to reach a point. It can't just go up and then to this point and then fall down. So what we need to do is we need to figure out what that's going to be at point B. So what I know is that since it's moving in a circle, it has to have some kind of centripetal acceleration or to keep it moving in a circle. So what that needs to be is that needs to be v squared over r. So that's going to be the centripetal acceleration. In this case, it's going to be big R because it has to move in that size of a circle. When that needs to actually be equal to the acceleration due to gravity. So see what the case here is that gravity has to be only force at this point pushing in a circle. We can't have the car go up to point B and feel a normal force because of we can't feel a normal force because that would not be the minimum. The minimum is where it just reaches that point and B is having no effect on it, where it's weightless in effect. So what this means is that we can then use this later to substitute into our equations. Okay, so what I'm going to do is I'm going to set up a conservation of energy equation. I'm going to write down what the initial energy is here at point A. So that's just going to be mass times G times H. And that's going to be equal to the potential energy here. So it's going to be mass times gravity, and the height here is 2r, since that's the diameter of this circle. And then I'm going to say plus 1/2 m, and then the velocity at b squared. So the velocity is going to be at different points here in the circle, so I have to specify that the velocity here at b is a specific point. And we note that at point B, that has to be the case here. So here we're going to have our VB squared is equal to GR. So now what we have is we have MGH equal to MG2R plus 1/2 MGR, which we're substituting it in. Okay. Then what I note is that we can cross out all these mg's, so it doesn't depend on mass of what the height is. So we have height is equal to 2.5 r as a minimum. Okay, so that's problem A. Problem B, if height is 3.5 r, so more than our minimum, and r is 14 meters, and since we have to compute the speed, real acceleration, and tangential acceleration of passengers when a car is at point C. So that's going to be when the velocity of the car is straight down, which is at the end of the horizontal diameter. So that's what that means there, end of the horizontal diameter. Show these acceleration components in a diagram, approximate the scale. Okay, so point B, I'm going to set up another conservation of energy equation. I'm going to write down MGH equal to MG. We have here at this point, the height is only R because it's only going up one radius. So R plus 1/2 MVC squared. So again, V is going to be different at point C compared to point B. Okay, so that's also what we're trying to find. So what I can do is I can then substitute in, actually I'll cross out m first. It's the same mass in each of those terms. So we have what h is, we were told is 3.5 r. So we have 3.5 GR equal to GR plus 1/2 VC squared. Okay, so then I can simplify this equation. So we have 2.5 GR. Then we're going to multiply by 2 to get rid of that 1/2. That's going to be equal to VC squared. So then what we have is 5 GR is equal to VC squared. Okay, then we can substitute what R is. That's 14 meters, and take a square root, and we should just get VC. VC is equal to 26.2 meters per second. I'm not sure why that's deleting. Okay, so that's our velocity, but the radial acceleration we're going to have is we're going to write down that our radial acceleration is equal to v squared over r. And so again, that's at point C. So then we can substitute what VC squared is. That's 5G over R. So at 5G R divided by R is equal to 5G. And we have our tangential acceleration. The block is not experiencing any normal force at all at point C, and it's going straight down. So that's tangent to the circle. So that should just be our gravitational force. And then what we can do is we can then show the acceleration in a diagram, approximately scale. I'm going to write down the curve at arc C. I'm going to show our car there. And then I'm going to show approximately the scale. We have 5G for AR. And then for AT, we have G. That should look like a G. So see here, we have a high G force towards the center of the circle. If you have any experience with being on a roller coaster, you definitely feel this force as you were traveling around the circle, a force pushing you towards the center of the circle.